Hello, hi dear friends, welcome to yet another session of Mission Bank. Yes, so this is the very first session of 10th CBSE Maths. Okay, as far as your syllabus is concerned, yes, we have to cover a total of 14 chapters. Yes guys, in all of these 14 chapters, yes, we have to deal with very simple and basic level concepts. Yes, honestly speaking, 10th CBSE Maths paper is not as tough as you guys think. Yes, once we start our classes or once we start our sessions, you will also start feeling the same and then you will agree with me, ma'am, you are right, actually we are dealing with very simple and basic level concepts. Yes, anyways, let's start our sessions. Let's start our sessions with the first chapter, real numbers. Mostly I'll be following the same order of the chapters, your same order your NCERT textbook has followed. Okay, so shall we start our session? So S, real numbers. The chapter real numbers is actually a very small and simple chapter. Here in this chapter, yes, you have to deal with two important properties of positive integers. The first one is Euclid's division algorithm and the second one is fundamental theorem of arithmetics. Yes, first we have to learn what actually these properties are, or we can say what Euclid's division algorithm states or what fundamental theorem of arithmetic states. So first we have to understand this, and then we have to deal with some of the major applications of these two properties, or some of the major applications of Euclid's division algorithm and fundamental theorem of arithmetics. Yes, so once we are done with these two things, our chapter is over. Is it clear, guys? Yes. So before going deep into the chapter real numbers, yes, let's do a quick recap of the chapter number systems, because we can say the chapter real numbers is actually an extension of the chapter number systems that you learned in your 9th grade. You will encounter so many terms in the chapter real number that you have already learned in the chapter number systems. So let's do a quick recap. Okay, so in the chapter number systems, first you learned about so many sets of numbers or so many collections of numbers. Yes, so let's discuss about them one by one. The first set of numbers is set of natural numbers. Yes, set of natural numbers is represented by the letter capital N, and set of natural numbers is actually a collection of numbers starting from 1, 2, 3 and it goes on forever. We know number has no ending, or we can say number never ends, isn't it? Yes, so we can say there are infinite number of numbers. Yes, so this particular set has no proper end point, it goes on forever like this. Is it clear, guys? Okay, so the next set is set of whole numbers. And set of whole numbers is represented by the letter capital W. Set of whole numbers is a collection of numbers starting from 0, 1, 2, 3, 4. It goes on forever. Is it clear, guys? Okay. Now the next set is a set of integers. So set of integers is represented by the letter capital Z. Set of integers includes negative numbers. 0 and positive numbers. Yes, and set of integers does not include fractions or decimal numbers. Is it clear, guys? Yes. Now let's see the next set. The next set is set of rational numbers. So set of rational numbers is actually a collection of all those rational numbers. So what are rational numbers? I'll write it first, then I'll explain it to you. Any number that can be represented in the form P by Q, where P and Q are integers, and Q naught is equal to 0. So any number that can be represented in the form P by Q. Okay, and here some conditions are there. Yes, while representing a number in the form P by Q, both P and Q should be integers and Q should not be equal to 0. Is it clear, guys? Yes. So let's take an example. Suppose let's take a number 100. So can we write the number 100 in the form P by Q? Yes, of course we can write the number 100 in the form P by Q, where you can see both 100 and 1, both P and Q are integers, and your denominator 1 is not is equal to 0. Here it is given Q should not be is equal to 0. Yes, here in this equation 1 Q is equal to 1. So yes, we know 1 is not is equal to 0. So we can say the number 100. The number 100 can be written in the form P by Q, where P and Q are integers and Q not is equal to 0. So we can conclude the number 100 is a rational number. Okay. So let's take another example. 3986. So can we write the number 3986 in the form P by Q? Yes, we can write 3986 in the form P by Q as 3986 by 1, where both of these numbers are integers and the denominator value is not is equal to 0. Is it clear, guys? So we can say the number 3986 is also a rational number. Yes. So in short, we can say all the integers, we know all the integers can be written, all the integers can be represented in the form P by Q, isn't it? Say for example, minus 36489, okay, minus 36,489. So this number is an integer, this number is an integer. So can we write this number? Can we write this integer in the form P by Q? Yes, we can write this number, isn't it? So minus 36489, 36,489 divided by 1. Now I represented the given number in the form P by Q, isn't it? Yes. And we can see both P and Q are integers and the denominator value is not is equal to 0. So we can conclude, or in short we can say all the integers are rational numbers. All the integers are rational numbers. Okay. Yes. So are only integers rational numbers? It's not like that. We can say some of the decimal numbers, only some of the decimal numbers are also rational numbers. So let's take an example. Suppose 9.98. So this is a decimal number, isn't it? Yes, this is a decimal number having 2 digits after the decimal point. Okay. So can we write this number? Can we write the given number, given decimal number in the form P by Q? Yes, we can write. We can write it as 998 divided by 100. Yes, and here we can see both the numbers 998 and 100 are integers. And also 100, the denominator value is not is equal to 0. So we can say 9.98 is a rational number. Again, let's take another example, 3.854. Okay, let it be 0.854. So can we write this decimal number in the form P by Q? Yes, we can write it as 854 divided by 1000. Where 854 and 1000 are integers and 1000 is not is equal to 0. So the given number 0.854 is also a rational number. So we can conclude set of rational numbers includes all integers and some decimal numbers. Not all numbers are rational numbers, but some numbers are rational numbers. Is it clear, guys? Not all decimal numbers are rational numbers, but some decimal numbers are rational numbers. But all integers are rational numbers. Yes. Okay. Yes. So just now we have seen some of the decimal numbers. Some of the decimal numbers can be written in the form P by Q, where P and Q are integers and Q not is equal to 0. That means Some of the decimal numbers cannot be written in the form. Some of the decimal numbers cannot be written in the form p by q, where p and q are integers and q naught is equal to 0. So what do we call such numbers? We call such numbers as irrational numbers. Yes, such numbers are known as those numbers that cannot be represented in the form p by q, where p and q are integers and q naught is equal to 0, are known as irrational numbers. So a collection of all those irrational numbers is a set of irrational number. Is it clear, guys? Yes. So set of irrational numbers include some decimal numbers. Okay. So say for example, root 2 is a irrational number. Root 2 is an irrational number. Root 3 is an irrational number. 0.987 ... is an irrational number, etc. Is it clear, guys? Yes. So in the chapter number systems, you didn't learn how to prove these irrational numbers are irrational, isn't it? Yes. So in the chapter real numbers, we'll learn about it. We'll discuss them in detail later. Okay. Yes. So now let's see the next set. So the next set is set of real numbers. So set of real numbers is represented by the letter capital R. And set of real numbers includes all the rational numbers and all the irrational numbers. Set of real numbers includes all the rational numbers and all the irrational numbers. Is it clear, guys? Yes. Okay. Yes. So you have already learned about number line, isn't it? Yes. So what is a number line? It looks like this. This is a line. The center there is 0. To the left of 0 we have positive real numbers. And to the right, to the right of 0 we have positive real numbers, and to the left of 0 we have negative real numbers. Yes. So we can say every real number represents a unique point on the number line. And every point on the number line represents a unique real number. Say for example, suppose we want to find the point representing the real number 1. You see, only this point represents only this point on the number line represents the value 1. No other point on the number line represents the value or represents the real number 1. Is it clear? Okay. Suppose let's consider this point. Maybe this point represents 0.5. Okay. Yes. So this particular point represents only the real number 0.5. Is it clear? It represents no other real number. Actually this point represents, this point is equal to, or this point represents only the real number 0.5. Is it clear, guys? Okay. Suppose if you are asked to find the point representing, real numbers like root 3, root 2, root 5, root 7, etc. How do you find the point representing? How do you find the points representing these kind of real numbers? Actually, it's very easy. For finding the point on the number line that represents these type of real numbers, we use Pythagoras theorem. Yes. So Pythagoras theorem states that the square of the in a right triangle, the square of the hypotenuse is equal to the sum of the squares of base and altitude, isn't it? If suppose h is the hypotenuse, If suppose h is the hypotenuse, we can say h square is equal to base is b square, and height let it be a, altitude a square. So we can say h is equal to, then h is equal to root of b square plus a square, isn't it? Yes. So here we have to find, the point. First let's find the point that represents root 2. Let's find the point that represents root 2. Okay. So let the length of the hypotenuse, be root 2. Yes. So we know 2 is equal to, 1 plus 1, isn't it? Or we can say, yes, 2 is equal to 1 plus 1, or otherwise we can say 1 square plus 1 square. So root 2 is equal to root of 1 square plus 1 square. Is it clear? Okay. Now on this number line, yes, I am going to consider these 2 points, 0 and 1. Okay, we can say the point 1, the distance between, these 2 points 0 and 1 is actually 1 unit. Okay, so let me consider this as the base of the right triangle. This is the base of the right triangle. Now I am going to draw a line, perpendicular to the point 1, whose length is also equal to 1 unit. Okay. Now I am going to join these two end points. Here I got a right triangle. So this one is the base of the right triangle. This is the height or altitude of the right triangle, and this is the hypotenuse. So what is the length of this hypotenuse? So the length of this hypotenuse is root 2. Is it clear? Okay. Now I am taking this distance. And now I am finding the point on the number line which is at a distance of root 2 units from 0. So you see here you got this point. This point represents root 2. Is it clear? Yes. You can use this. Same method for finding the point representing root 3, root 5, or root 7, or root 13, root 11, etc. Let's see one more example and then let's move on to the next topic. If suppose you want to find the point representing 3. So then we know root 3 is equal to root 2 the whole square plus 1 square. Is it clear? Okay. Now again on this number line, now I am going to consider the base length as root 2 units. Now I am going to consider the base length as root 2 units, and I am going to draw a line perpendicular to root 2. Now I am going to join these two end points. So I got a right triangle whose base length is root 2 and whose the length of altitude is equal to 1 unit, and the length of hypotenuse is equal to root 3. So I am taking this distance. Yes, with the help of a compass. Okay, yes, you can use a compass for that. Yes. Now I am going to find the point representing. Now I am going to find the point at a distance of root 3 from 0. So this will be the point root 3. Is it clear, guys? Similarly, you can find for root 5. So we can say root 5 is equal to root 3 the whole square. Root 3 the whole square plus root 2 the whole square. Root 3 the whole square plus root 2 the whole square. Isn't it? Yes. So you can take the base length as root 3. You can take the base length as root 3 units with the help of a compass. Yes, you can find the point at a distance of. With the help of a compass, yes, you can find the point at a distance of root 2 units from the point root 3, and you join these 2 points. Yes, you draw a perpendicular line. Yes, to the point root 3. In such a way, yes, the 2 end points are these 2. Is it clear? Then you can draw these 2 end points, so you will get a hypotenuse whose length is equal to root 5 units. So take that distance in the compass, find the point on the number line that represents the, that is that is at a distance of root 5 units from the point 0. Is it clear, guys? Yes. Okay. So So that's all about different sets or different collections of numbers. Okay. Now let's try to understand. Now let's discuss some more about these real numbers. Now we all know real numbers can broadly be classified into two as rational numbers and irrational numbers. Okay. If you are given an integer and you are asked whether the given number is a rational number or irrational number, yes, you can answer it immediately. You can answer it immediately. Means the given number is a rational number because it is an integer. Okay, yes. I told you earlier, only some decimal numbers are. Only some decimal numbers are rational numbers and some other decimal numbers are irrational numbers, isn't it? Yes. So if you are given a decimal expansion, how do you find, or if you are given a decimal number, how do you find whether the given number is a rational or irrational number? Yes. Now let's see, how do we find whether a given decimal number is a rational or irrational number? Yes, I'll write it first, then I'll explain it to you. If the decimal expansion of a number is either terminating or non-terminating but recurring, then the number is a rational number. Okay. And if the decimal number, if the decimal expansion of a number, or yes, if the decimal number given is non-terminating and non-recurring, then the given decimal number or then the given number is an irrational number. Is it clear, guys? Yes. Now let's understand some terms given in this. Point. Okay. First one is terminating. Second one non-terminating. Third one recurring, and fourth one non-recurring. Okay. Yes. So decimal numbers can be, or we can say there are so many types of decimal numbers. Or we can classify decimal numbers into so many based on the number of digits. Or based on the digits, not only number of digits, we can say based on the digits after the decimal point. Yes. So one kind of such classification is terminating and non-terminating, and the next one is recurring and non-recurring. So first let's understand what are terminating and non-terminating decimal numbers. Yes. So let's try to understand this with the help of an example. 3.986, 0.79, 2.386, 3865. Here 9.7967, 7968, 3.0043, okay, 0.974, etc. Okay. So here I have written here on this board, yes, I have written two sets of decimal numbers, isn't it? Yes. So in the first set of decimal numbers, yes, you can see there are only finite number of digits. After the decimal point, isn't it? There are only finite number of digits after the decimal point. In the first decimal number there are only 3 digits. In the second decimal number there are only 2 digits, and in the third decimal number there are only 4 digits. Is it clear? Okay. Yes. That means we can say the given decimal numbers have some proper or some fixed end point. Is it clear? Okay. Now let's consider these three examples. Now let's consider these three decimal numbers, and in all of these decimal numbers you can see there are infinite number of digits after the decimal point. There are infinite number of digits. Dot 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 means it goes on forever like this. Is it clear? So we can say there are infinite number of digits after the decimal point. So in all of these given decimal numbers, in all of these three given decimal numbers, we can say they don't have a fixed end point. Is it clear? Okay, yes. Those decimal numbers having some fixed end point, or those decimal numbers that have only finite number of digits after the decimal point are known as terminating decimal numbers. Is it clear? Okay. And those decimal numbers who have infinite number of digits after the decimal point is known as non-terminating decimal numbers. Is it clear, guys? Okay. Now let's see what actually this recurring and non-recurring decimal number. Okay. Yes, okay. Again, let me write some examples. 3.999, it goes on forever. 7.656565, it goes on. 18.932932, it goes on. Again, another set of examples. 8.5678, it goes on. 0.9768, it goes on. 15.00596, it goes on. Again, on this board I have written two sets of decimal numbers. Okay, so let's analyze these two sets of decimal numbers. Okay, in the first collection, or in the first set of decimal numbers, yes, you can see a set of numbers, either a single number or a set of numbers, either a single number or a set of numbers is getting repeated uniformly. Here you see the number 9. Here the number 9 is getting repeated. And again, here the number 65. Here the number 65, or we can say set of two numbers 6 and 5 are getting repeated uniformly, like 65, 65, 65. Is it clear? Similarly, here the number 932, or else we can say a collection of, or a sequence of three numbers 932 is getting repeated uniformly. Is it clear? Okay. Now let's consider the next three examples. Here there is no repetition of digits. Is it clear? Okay. Those decimal numbers in which the sum of we can say yes, those decimal numbers in which either a single number or a sequence of numbers or a set of numbers is getting repeatedly in a uniform manner, such decimal numbers are known as recurring decimal numbers. And those decimal numbers in which no digit or no number or no sequence of number is getting repeated, we call such decimal numbers as non-recurring decimal numbers. Is it clear? Okay. So here we learned 4 types of decimal numbers. The first one is terminating decimal number, second one is non-terminating decimal number, third one is recurring decimal numbers, and fourth one is non-recurring decimal numbers. Yes. Now back to our point. If the given decimal number or if the decimal expansion of a given number, if the given decimal number or if the decimal expansion of a given number is either terminating or it is non-terminating but recurring, then we can say the given number or the given decimal number is a rational number. If suppose the given decimal number or the decimal expansion of the given number is non-terminating and also non-recurring, then we can say the given number is an irrational number. Say for example 0.976. This is a terminating decimal number. Yes, so we can say this is a rational number. This is a rational number. Again 9.666, it goes on. Yes, even though the given decimal number is a non-terminating decimal number, it is a recurring decimal number. Why? Because yes, the digit or the number 6 is getting repeated in a uniform manner or uniformly, isn't it? So we can say the decimal number 9.6666 etc. is a rational number. This is also a rational number. Again another example 10.09164, it goes on forever. Here the given decimal number is non-terminating and also the given decimal number is non-recurring. So we can say the given decimal number is an irrational number. Is it clear, guys? Yes. So is it clear how to find? Whether the given decimal number is a rational or irrational number? Yes, fine. Okay. Now let's discuss some important properties or points, some points regarding real numbers or some points regarding rational and irrational numbers. Okay. So the first one, if we add or subtract a rational number and an irrational number, then the result obtained will be irrational. Okay, so let's see some examples. Suppose we know 2 is a rational number. Again, root 2 is an irrational number. Now we are going to add these two numbers. So the result obtained is 2 plus root 2, which is an irrational number. Yes. So this is an example for addition. Suppose we are subtracting root 5 from root 9, not root 9, 9. So here 9 is a rational number and root 5 is an irrational number. So when we are subtracting a rational number when we are subtracting or when we subtract, when we add or subtract, yes, anyways, okay. So here we are subtracting root 5 from 9. Here we are finding the difference between 9 and root 5. So the result obtained is 9 minus root 5. So 9 minus root 5 is an irrational number. So that's what given in this point. Is it clear, guys? Okay. Again, the next point. So if we multiply or divide a non-zero rational number by an irrational number, then the result obtained, non-zero rational number by an irrational number, then the result obtained will be irrational. Yes. Here it is given a non-zero rational number. Why it is given so? We all know it is given so because 0 0 multiplied by or 0 divided by any other real number. It can be a rational number or else it can be an irrational number. The result obtained will be equal to 0, and we all know 0 is a rational number, isn't it? Yes. So that's why it is given here. When we multiply or divide a non-zero rational number and an irrational number, then the result obtained will be irrational. Is it clear? If we multiply or divide 0 by an irrational number, then the result obtained will be a rational number, because the result obtained is always is equal to 0. Is it clear? Okay. So now let's discuss. Now let's see some examples. So here we are multiplying a rational and irrational number. So let 10 is a rational number, and we all know root 5 is an irrational number. So now we are multiplying these two numbers. The result obtained is 10 root 5, where 10 root 5 is an irrational number. Is it clear? Okay. One example for division also. See, 10 divided by 5 root 2. So here I am dividing the rational number 10 by an irrational number. Let's see, the result obtained is equal to root 2, where root 2 is an irrational number. Is it clear, guys? Okay. Okay. Okay, so far we discussed about the summation of a rational and irrational, or difference of a rational or irrational, or product of a rational or irrational, like rational and irrational, isn't it? Yes. Now what if we add, subtract, multiply or divide two irrational numbers? Let's see. If we add, subtract or multiply or divide two irrational numbers, then the result can either be a rational number or an irrational number. So here in this case, when we add, subtract, divide or multiply two irrational numbers, the result, there are two possibilities. Either the result can be an irrational number, or else the result can be a rational number. Yes. So let's see. First, for addition. Suppose we are adding root 3 and root 3. Okay. So the result obtained is 2 root 3, where 2 root 3 is an irrational number. Okay. Again, if suppose we are adding root 3 and minus root 3. We are adding root 3 and minus root 3. The result obtained is 0, where 0 is a rational number. Okay. Now let's see two examples for subtraction. Suppose we are subtracting root 3 minus root 3. Yes, here we are subtracting root 3 from root 3. The result obtained is equal to 0, which is a rational number. Again, if we are finding the difference between root 5 and root 3, the result obtained is root 5 minus root 3, where root 5 minus root 3 is an irrational number. Okay. Now let's see some examples for multiplication and division. Suppose we are multiplying two irrational number root 3 and root 3. The result obtained is equal to 3, where 3 is a rational number. Again, if suppose we are multiplying root 3 into root 7, the result obtained is 21. The result obtained is 21, and we know 21 is an irrational number. Okay. So let's see two examples for division. Suppose we are dividing two irrational number, Root 5 by root 5 is equal to 1, where 1 is a rational number. Again, if we are dividing 10 divided by root 5. So when we divide 10 by root 5, the result obtained is 2 root 5. The result obtained is 2 root 5, where 2 root 5 is an irrational number. So that is what is given here. That's what it is given here. When we add or subtract, divide or multiply two irrational numbers, the result can either be a rational number or it can be an irrational number. Is it clear, guys? Okay. Fine. So now let's see the last topic of the chapter, number systems. Yes. So I told you every real number represents a unique point on the number line, and every point on the number line represents a unique real number. Suppose you are asked to find the points representing these kind of real numbers, like 1 by root 2, 3 divided by 5 plus 10 root 2. Now 10, let it be 6, and here also 5. Okay. 7 divided by 15 minus 3 root 2, etc. If you are asked to find the points representing these kind of real numbers, is it easy to find the points representing these kind of real numbers? Honestly speaking, it is very difficult to find. It is very difficult to find the points representing these kind of real numbers if you retain these real numbers as such. Why? Because why? Because the denominators of these given real numbers, the denominator of these given numbers real numbers are irrational numbers, not rational numbers. It will be much more easier for us to find the point representing a real number, when the denominator of the real number is a rational number. Is it clear, guys? Yes. So here can we convert? Can we convert the irrational number here? Can we convert the irrational number in the denominators into rational numbers? Is it possible? If it is possible to convert the irrational number into a rational number, then it will be easier for us to find the points representing these real numbers. Is it clear, guys? Yes. The answer to the question, whether we can convert the irrational number in the denominator into a rational number is yes. We can convert the irrational number in the denominator into a rational number, that too without changing the actual value of the real number, Is it clear? It is possible. Now we are going to discuss about this process. That is, what do we call this process? And how do we perform this? What do we call this process, and how do we convert the irrational number in the denominator into a rational number? Yes. So I'll write it first. Okay. The process of converting the irrational number in the denominator into a rational number without changing the actual value is known as rationalizing the denominator. So what do we call this process? This process is known as, or this process is called as rationalizing a denominator. While rationalizing a denominator, while converting an irrational number in the denominator to a rational number, yes, we have to make sure that the actual value of the real number remains unchanged. Is it clear, guys? Yes. So what do you mean by rationalizing a denominator? Yes, I'll write it here. If the denominator of an expression, if the denominator of an expression contains a term with a square root, yes, or a number under any radical sign, as far as your syllabus is concerned, yes, we need to consider only about square root terms. Okay, yes, term with a square root, then the process of converting the expression into an equivalent expression. Equivalent expression means what? Equivalent expression means the actual value of the expression remains unchanged. We have to convert the denominator. In such a way the actual value of the expression remains unchanged. Is it clear? Okay. Whose denominator is a rational number. Is known as, if the denominator of an expression contain a term with a square root like this. Okay. Then the process of converting the expression into an equivalent expression whose denominator is a rational number is known as rationalizing the denominator. Is it clear, guys? Okay. So how do we find an equivalent expression of the given expression? Say for example, if let's take an example, let's take a fraction 3/4. Yes, in school classes, maybe in your UP/LP classes, yes, you have learned how to find an equivalent fraction of the given fraction, isn't it? Yes. How do we do that? We multiply both the numerator and denominator by a same value. Say for example, if I am multiplying both the numerator 3 and the denominator 4/4, then I will get an equivalent fraction. Isn't it? Yes. Whose actual value is equal to 3/4. Is it clear? We can say 3/4 is equal to 12/16. The actual value of these two fractions are one and the same. Why is it so? Because we are multiplying both the numerator and denominator of the given fraction by a same number. When we multiply both numerator and denominator of a fraction by a same number or by same expression, okay, by a same number or by same expression, actually there we are multiplying by 1, isn't it? 4/4, here we are multiplying both 3 numerator 3 and denominator 4/4. So we can say we are multiplying the fraction 3/4 by another fraction 4/4. So we know 4/4 is equal to 1. So actually we are multiplying 3/4 by 1. Is it clear? Yes. Similarly, when you are given these kind of real numbers, for rationalizing the denominator, for rationalizing the denominator of these kind of real numbers, we have to multiply both the numerator and the denominator by some same value. Is it clear, guys? Okay. Now yes, okay. So now we know for finding the equivalent expression, we have to multiply, or for rationalizing the denominator, we have to multiply both numerator and denominator by some same value. Okay. So now the next question is, how do I find that value to be multiplied? How do I find that value to be multiplied by? Yes, and for that it is also very easy, and for that we use an identity, and the identity is, we all know, identity a plus b into a minus b is equal to a square minus b square. Is it clear? Yes, actually we use this identity. For finding the value. Or else we can say we use this identity for rationalizing the denominator. Okay, let's see how do we rationalize a denominator using this identity. Okay. So some may think, why cannot we multiply these real numbers by any random value? You see, if we multiply the given real numbers by any random value, okay, if you are multiplying both numerator and denominator by any random value and same value, yes, you can find an equivalent expression. But maybe not always you can rationalize the denominator. Is it clear? Yes. So we use this particular identity for rationalizing the denominator. Is it clear? Okay, let's see. So here in this identity, we have two terms. Here in this identity we have two terms. One is a plus b and the other one is a minus b. Is it clear? Okay. So now let's analyze these examples. Here the denominators of all of these three given real numbers, some are in the form a plus b and some are in the form a minus b, isn't it? Here in this example, the denominator is in the form a plus b, and here in this example the denominator is in the form a minus b. Even though here there is only one term, isn't it? We can assume root 2 either as root 2 plus 0 or as root 2 minus 0. We can assume, or we can write this root 2 as either as root 2 plus 0 or root 2 minus 0. Is it clear? So simply we can say the denominators of these kind of real numbers will be either in the form a plus b or else in the form a minus b. Is it clear? Okay. If the denominator of the given real number is in the form a plus b, then you have to multiply both the numerator and denominator by the a minus b form of the given denominator. And also, if the denominator of the real number is in the form a minus b, then you have to multiply both the numerator and denominator by the a plus b form of the denominator. Yes. So let's try to understand this with the help of an example. Okay. So let's take this same example. Here let's consider this real number. So the real number is 3 divided by 5 plus 6 root 5. Yes, we know in the denominator there is a term with a square root. So we can say the denominator of the given real number is an irrational number. Now here we have to rationalize the denominator, means we have to convert the irrational number into a rational number without changing the actual value of the real number. So for the actual value to remain unchanged, okay, we have to multiply by same value. Okay. And here Here I told you for rationalizing the denominator we use the identity a plus b into a minus b is equal to a square minus b square. And also if the denominator is in the form a plus b, then you have to multiply by a minus b. Here in this example, the denominator is in the form a plus b. So we can say a is equal to 5 and b is equal to 6 root 5. Is it clear? Now what is a minus b is equal to? A minus b is equal to 5 minus root 5. Now I got the a minus b form of the given denominator. So I have to multiply both the numerator and the denominator by this a minus b form, that is 5 minus 6 root 5. So 5 minus 6 root 5, I am going to multiply both the numerator and the denominator by 5 minus 6 root 5. Okay. So let me multiply. Let me open the bracket. So 3 into 5 minus 6 into 3 means 18 root 5. So our numerator becomes, so after multiplying the numerator 3 by 5 minus 6 root 5, our numerator becomes 3 into 5 minus 18 root 5. Now coming to the denominator. Here in the denominator part you can see we have to multiply 5 plus root 5 into 5 minus root 5. 5 plus root 5 into 5 minus root 5. Isn't it? Yes. So here we can use that identity. Here it is given in the form a plus b into a minus b. So we know a plus b into a minus b is equal to a square minus b square. Here a is 5 and b is 6 root 5. So a square is 25 minus b square means 6 square into root 5 the whole square, that is equal to 25 minus 36 into 5. So 25 minus 36 into 5 means 25 minus 120. 25 minus 120. 120 minus 20 is 100. Again, when we subtract 5 from 100, the answer is minus 95. So minus 95. Okay. So here I am going to multiply this minus 1. Here I am going to multiply this numerator by minus 1. Okay. Yes. So we will get 18 root 5 minus 15 divided by 95. Yes. Now you can see that we have rationalized the denominator. We converted the irrational number in the denominator into a rational number without changing the actual value of the expression or actual value of the real number. Is it clear, guys? Okay. So now let's see the next example. When the denominator is in a minus b form. When the denominator is in the a minus b form, yes, we have to find the a plus b form and then we have to multiply both the numerator and denominator by the a plus b form of the denominator. So 7 divided by 15 minus 3 root 2. So I am going to multiply the a plus b form of the given denominator is 15 plus 3 root 2. So I am going to multiply both numerator and denominator by 15 plus 3 root 2. Okay. So here let me open this bracket. 7 into 15 means 105. 105 minus 21 root 2 divided by here the given expression, here the expression is in the form a plus b into a minus b. We know a plus b into a minus b is equal to a square minus b square. So here a is 15, so 15 square is 225 minus 3 root 2 square means 3 square is 9 and root 2 square is 2, so we will get 18. So when we find the difference between 225 and 18, so 225 minus 5 is 220. Minus 10 is 210, again minus 3 is 207. So 105 minus 21 root 2 divided by 207. Now we have converted the irrational number in the denominator into a rational number without changing the actual value of the given real number. Is it clear? We have rationalized the denominator. Is it clear? Okay. Okay. So here in the first example, Yes, there is only one term in the denominator. There is only one term in the denominator, isn't it? Yes. So to rationalize such numbers, yes, you can simply multiply. You can simply multiply both the numerator and denominator by the irrational number given in the denominator. Here, you can multiply both numerator and denominator by root 2 because the denominator of the given real number is root 2. So we will get root 2 by 2. Is it clear? Or else you can consider this root 2, this given root 2 either as root 2 plus 0, or else you can consider root 2 minus 0. Okay, yes. Now here you can see the denominator is in the form a plus b. So you have to multiply by a minus b. So root 2 minus root 2. Root 2 minus 0. Okay. So okay, I'll open the bracket. So here I'll get root 2. Here I'll get root 2 square minus 0, that is equal to root 2 by root 2. Similarly, here you have to multiply root by root 2 plus 0. So when I open the bracket, I'll get, in the numerator I'll get root 2, and in the denominator I'll get root 2 the whole square minus 0, that is equal to 2. Yes, either you can do like this. There is no need of doing all these complex calculations, all these things. You can simply multiply. You can simply multiply both the numerator and denominator of the given real number by the irrational number given in the denominator when there is only one term in the denominator. Is it clear, guys? Yes. Okay, fine. Okay, so that's all about the chapter. That's all about the chapter number systems. Yes, is everything clear to you guys? Yes. If you have any doubts, yes, please feel free to ask in the comment section. Okay. So let's wind up. This recap session. And let's move on to the next topic, or we can say now let's discuss the chapter real numbers. Yes, okay. Now let's discuss the chapter real numbers, and the first topic that we are going to discuss is Euclid's division algorithm. Euclid's division algorithm.